Hello everyone. For this tutorial video, I like to talk about how permittivity relates to saturation, and how this is different for different cores. In particular, we would graph the nonlinear effect of permittivity by doing field intensity on the horizontal part of the graph, which is the independent variable, and the flux density on the vertical part of the graph, which is the dependent variable. And the reason why we chose these two variables specifically compared to each other is because these properties are independent of the overall size of the magnetic field or magnet itself, which would not be true for something like field flux. So we choose the strategy of using flux density and field concentration or intensity over a particular region, so that we get more objective results than if we had other variables to worry about, like the size of the magnet. When we test different materials, the graph looks like this, and we can see clearly that the relationship is nonlinear, because it increases sharply on a curve at first, and then stops at a particular point, or becomes very slow to the point of stopping if it doesn't stop entirely. And the technical term for the point when it stops is called saturation. An explanation of why this happens is that at the beginning of the test, there are many atoms available to align themselves with the magnetic field. But as more atoms get used up, there is less available because you cannot magically create more atoms. So this logically means there's more magnetomotive force needed overall to get less and less flux. However, saturation is only a problem for iron core magnets because of how iron is a great conductor of magnetism compared to other materials. So because something like an air core magnet, for example, does not conduct magnetism as severely, saturation will not be as much of an issue. And another problem besides saturation is something known as hysteresis, which is the tendency of a ferromagnetic material or something similar to stay magnetized after the magnetizing force is removed. So we will see, for example, that if we apply a force as we did in the first test, but this time reverse the direction at the endpoint, we will get a lag like this. And if we go back from the second endpoint, we will get another built-in lag, which we will have to graph out. Although hysteresis seems like a problem normally, it can actually be beneficial in something like a hard drive disk, because of the natural tendency for the magnetized object to remember its state. So that is why hard drives are often magnetic in order to store information in a very long-term manner. And hysteresis is also good for filtering out high frequencies, like in radio broadcasting, because there must be extra energy consumed to overcome the hysteresis of the magnet. And just like with saturation curves, hysteresis curves are different for different materials. There is no one right answer for all of them. Now that I've explained how saturation and hysteresis work, I can explain another popular application of electromagnets, which is called induction. It is actually the basis of how many electrical generators work, like turbines and power plants. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.